So a parallel circuit is a circuit with multiple paths through the circuit. So what electrons do when they go through a circuit is they go from the well, what charges do is they go from the positive end to the negative end. And so this is a typical capacitor circuit. I have a voltage here, and I have a capacitor here. And so this just charges this thing up. And there's only one thing that the charges can do. In parallel, I'm giving it multiple paths. So I might have another capacitor. So I'll call this C1 and C2. I'll try to make C2 look a little different, right? And then I might also have a C3. Trying to make them all look different. And so this is capacitors in parallel. The charges can do this or that or that. The thing to remember about this is that all of these guys have the same voltage across them. That is because these are wires and connected by conductors. The same voltage is across this, as is across this, as is across this, because each of these guys is connected by a wire to the ends of the battery. And so I'd say, normally I say Q is equal to CV, or I could say V is equal to Q over C, right? And so I could say, look, I could say V1 is equal to Q1 over C1. That is to say, this guy gets charged Q1, this guy gets charged Q2, and this guy gets charged Q3, right? They've got different capacitances, and so even though they have the same voltage, they maybe have different charges on them. And so V2, the voltage across this guy, is equal to Q2 over C2, and V3 is equal to Q3 over C3. Right. Now suppose what I want to know is the capacitance of the whole thing. So imagine this thing was just a giant black box or red box, and I couldn't see in it, and all I know is it acts like a capacitor, a parallel plate capacitor of some kind. So I want to find the equivalent capacitance. Right, and so then I would say, well, the capacitance of the whole thing I'm just going to call C parallel, right? And so I'm going to say Q tote is equal to C parallel times V, right? Because I'm applying this voltage, the voltage of the battery, across the whole thing. Right. Well, what is Q tote? Q tote is equal to Q1 plus Q2 plus Q3. That's the total charge that ran onto these capacitors, right? Well, Q1, if I just rearrange this equation, is C1V1. Q2 is equal to C2V2, and Q3 is equal to C3V3. But to circle all the way back, these V's are all the same. We just said at the beginning that this guy has the same voltage as this guy and this guy because the battery is connected across all three. And so that's C1V, C2V, C3V. Right? And that means that CP times V, that is to say Q tote, which is that guy, is equal to C1V plus C2V plus C3V. Now all of the V's are the same and they all cancel, and so I get the parallel capacitance is C1 plus C2 plus C3. Capacitors in parallel add to get total capacitance. Maybe I should put that up just a little bit so you can see it. So I could say, by the way, it didn't matter how many I had. You can try that with 2 or 6 or whatever. The math comes out the same. I just picked 3. And so the total capacitance of 3 capacitors, 20, 30, and 60 microfarads in parallel, is just 20 microfarads plus 30 microfarads plus 60 microfarads, or 110 microfarads. So now we're talking about capacitors in series, and so I have to just mention briefly what a series circuit is. Capacitors in series is in a series circuit, there's only one way through the circuit. Right? So I have a battery. This is my C1, this is my C2, and this is my C3. And let's just talk about this for a second, what happens here, right? We already said that the way a battery works is it's a pump. And so it's grabbing positive charges off here and sticking them up on here. Technically what it's doing is, as I've said a few times, this is pulling electrons the other way. But you can talk about it either way. But the point is, however many charges get pulled off here are stuck up here, or vice versa. And so if this guy gets a bunch of positive charges, this guy gets an equivalent number of negative charges. And as far as direct access is, that's all the battery can do. It can put stuff on this plate or this plate. It has no access to these guys because there's a gap there and the charges can't run across the gap. And so if this guy gets a charge plus Q, this guy gets a charge minus Q. That's just what happens. And since capacitors always have the same charges, this guy will attract a minus Q from this guy onto this guy. This is a conductor here, right? This is a metal plate, a wire, and another metal plate. Minus Q. That leaves a plus Q on this plate, which puts a minus Q on this plate, which puts a plus Q on this plate. So capacitors in series right, whereas capacitors in parallel all have the same voltage, capacitors in series all have the same charge. And so I can say Q1 equals Q2 equals Q3 equals Q. They do not all have the same voltage. Remember when I had parallel capacitors, right? They were all connected to both ends of the same battery. Right, and so the battery, there's a wire from each end of the battery to both of these plates, there's a wire from the end of the battery to both of these plates, and so on. They all have the same voltage. This is not the case with series capacitors, right? Series capacitors, the bottom wire is connected to this guy, which is not connected to this guy. And so while these guys have the same charge, they don't have the same voltage. V1 is not equal to V2, not necessarily anyway, not equal to V3. Right. And so, what is the same? This guy has a V1, this guy has a V2, and this guy has a V3. That is to say, when these guys are charged up, the total voltage across all the plates, voltage across this guy plus the voltage across that guy plus the voltage across that guy, is equal to the voltage across the battery. Since they're connected by a wire, this voltage is equal to that voltage, which means you can add up the potential energy per charge here, here, and here, and you'll get another way of saying is the potential energy to go all the way across the thing is just the sum of the potential energies across each capacitor. And so that says that the battery voltage is equal to V1 plus V2 plus V3. Right? And now we can ask the same question we asked of the parallel capacitors and say, well, suppose I want to treat this, right, as just some series capacitance. It's in a giant red box, and I can't see inside. I just see that wires go in. And so I want to know how this capacitance of the whole box relates to the individual capacitances. And I can say, well, look, I can write down my usual Q is equal to CV. That's just for any capacitor, right? And so the series capacitance, Q series, the amount of charge that runs onto this capacitor, my red box, is just equal to the series capacitance, whatever capacitance is held inside that box, times the voltage on the battery. Now here's the thing. The charge that runs onto the red box is actually just Q, because we just said that the amount of charge that runs in is just going onto these two plates, right? And so as far as I know, I just have Q running onto here and minus Q running onto here, which says Q is on the capacitor. So my Q series is just Q, and that's equal to C series times V, right? And so that means, so now I can write V is equal to Q over C series. But I can do that for each one of these. And so I can say, look, V1 is equal to Q1 over C1. V2 is equal to Q2 over C2. V3 is equal to Q3 over C3. But of course, there is no Q1. They're all just Qs, because all these guys carry the same charge. And so now I have V1 is equal to Q over C1, V2 is equal to Q over C2, V3 is equal to Q over C3. If I go back to this equation and substitute the Q overs, I get Q over C series is equal to Q over C1 plus Q over C2 plus Q over C3. Right, all the same Qs. And so I can cancel all the Qs, and that says 1 over C series is equal to 1 over C1 plus 1 over C2 plus 1 over C3. In other words, if I want to add up the capacitances of a bunch of series capacitors and get their total capacitance, their total series capacitance, I just add up 1 over all the capacitances, and that'll get me the series capacitance. So in our previous example, I can just say, look, I can say C1 is 20 microfarads, C2 is 30 microfarads, C3 is 60 microfarads. When they're in parallel, we added them up and we got 110 microfarads. But now we say in series, these same capacitors we can do this in our head if we want to, because we can find a common denominator, right, of 60. And so we can say 3 over 60 microfarads plus 2 over 60 microfarads plus 1 over 60 microfarads. C series is equal to 6. Oh, ooh, I'm sorry. This is still 1 over C series, right? That was our formula. 1 over C series equal 1 over C1 plus 1 over C2 plus 1 over C3. So this is 1 over C series, 60 microfarads. That says C series is equal to 10 microfarads. And notice in parallel they add up. In parallel I got 110 microfarads. In series I get 10 microfarads. Basically every time you add a capacitor in series, you decrease the total capacitance, because basically you're just moving the plates farther and farther apart. The two plates that are getting charged are these two. Every time you stick in another capacitor, you're just kind of pushing things farther away, and that makes it harder and harder for the charges to stick together. And so we get a much smaller capacitor when these guys are we get a much smaller capacitance when these guys are in series.